Okay, so welcome everyone. I'm Miguel Ángel González de la Torre. I'm here to talk about our presentation to this Congress, CISIS Congress, and that we made in collaboration Luis Hernández Encinas, Araceli Quiroga-Dios, and of course me. It's about the FO transformation, the Fujisaki Okamoto transformation in the NIST, applied to the NIST post-quantum code-based algorithm. So briefly, the parts of these presentations are these four. I'll briefly introduce post-quantum cryptography. Then I will explain how is the transformation, what's its definition, and then how it is applied to the code-based algorithms. Finally, of course, I will drag some conclusions and talk about future works. So as I was saying, we'll know that quantum computation and quantum computers suppose a threat to the current security of our system and our current cryptography. And the problem is that it breaks the mathematical background used today for our security, as I was saying. So we need a new mathematical background. There are several problems that are being studied and are already established for being a standard that maybe we hope for a long time resistant to resistant against quantum adversaries. It's in this landscape that the National Institute for Standards and Technology in the USA started a call to establish new standards in the categories of public key encryption and digital signatures. I'll focus today in the public key encryption side. So the Fujisaki Okamoto transformation historically was a structure or a way to define a highly secure hybrid encryption scheme. This is a scheme that uses both public encryption and symmetric encryption, but newer version of it became a way that we can construct a highly secure key EM. That means a key encapsulation mechanism. It's basically an algorithm to perform a key exchange, and the security that is reached is indistinguibly against chosen ciphertext attacks that is considered by the NIST as the standard security and the desirable security to reach. So the steps that we will follow are the one presented in the screen. We have a mathematical problem with a higher computational cost to break. We build a public key encryption scheme around this mathematical problem, and then we apply the transformation to reach a even higher security and a final key encapsulation mechanism. This is very relevant in post-quantum algorithm because all of the candidates to the NIST call in this category of public key encryption use this transformation to reach the security that I was referring to, the indistinguibility against chosen ciphertext attacks. So, in what consists the version of the transformation applied to the NIST algorithm? Okay, so in an article published by Hofheim and two other authors, they introduce a modular analysis of this transformation in which it's separated in two basic transformations. First, the transformation T, that is just a basic transformation applied to probabilistic encryption schemes to make them deterministic. This means that several encryption schemes have a randomness used as an input of the algorithm, and this will make this randomness deterministic. The other basic transformation is the transformation U, that is written here with an asterisk, because it's susceptible to several modifications. That depends on the use we want to do it, or the security we want to assume for the public encryption scheme that is underlying the transformation. So this is a key encapsulation mechanism construction introduced by Dent, but as I was saying, it might be modifiable in several ways that may transform this basic transformation in a very complex one. This is this basic scheme of the encapsulation and the decapsulation of this U transformation. In this case, we use the notation with the bot symbol because, as you might appreciate, in the decapsulation, if there is an error, the algorithm returns like the bot symbol. That means there has been an error. We might also return a pseudo-random value In this case, we will say that the transformation is designed with implicit rejection. Also, the M denotes that the shared secret that is reached, denoted by the letter key, only depends on the message M, or a randomly chosen message M. So now we'll talk about how this transformation applied to the code-based algorithms. The first one is classic McEllis that applies the QU transformation with implicit rejection. As I was saying, that means that in case of error, there is returned a pseudo-random value. The Q, the Q means that the algorithm uses an additional hash, kind of like a signature of the shared secret that is also checked for if there has been any errors or in case that there is a attacker sending message to the decapsulation. The public encryption scheme that is underlying the transformation in the case of classic McEllis has very valuable properties for the appliance of the transformation. In this case, that is deterministic and perfectly correct. Both these properties allow us to apply particular versions of the transformation that has good security reductions. And finally, this is kind of a conclusion we can already drag, that is that the use of additional hash initially was considered to reach security in a quantum oracle model. But today there are several security reductions in this model, in a quantum random oracle model, without the additional hash. So it might not be needed. The second code-based algorithm is the algorithm called BIKE that uses the FO transformation with implicit rejection. This is the most commonly used transformation used in the NIST candidates, and in particular in the lattice-based candidates is the one that is used in more of them. The BIKE algorithm is particular in the fact that its correctness depends on the decoder used, and the viability of the transformation also depends on the correctness of the algorithm. If the algorithm fails too much, we cannot apply the transformation and ensure the security of the system. So the developers propose another setup with what is called ephemeral keys. This means that for each key exchange, for each shared secret, we generate a new key pair of public key and secret key. And this might be interesting even for other things. The last code-based algorithm that we have studied is HQC. HQC applies the QFO transformation with explicit rejection. The Q means, as I was saying earlier, that it uses an additional hash to sign the shared secret. And it's very interesting that this algorithm uses this transformation because it's the only one in the third round of the NIST call that uses a transformation with explicit rejection. This might be an issue from a security standpoint, but also has some benefits in other areas that have not been that well studied. And finally, there might be a gap in the security reduction of this algorithm because the source that they quote, that is the Hofheim publication, doesn't have the security reduction of this transformation in particular, has the security reduction with the implicit rejection case. So finally, our conclusions of this topic are that code-based algorithms are here to stay, and they are very relevant. Actually, the NIST has already said that they want to establish a code-based standard for post-quantum cryptography. Also, we might expect the versions of this transformation to change in the code-based algorithms because some of them use, as I was saying, additional hash that may no longer be needed. In the case of classic McEllis, it might be very interesting to study the possibilities of avoiding using re-encryption. Re-encryption is when in the decapsulation you encrypt the message again to check if there has been any error. This is a vulnerability from a side channel attack point of view, so it might be interesting to use the good properties of the classic McEllis encryption scheme to avoid this step. And also, as I was saying before, the ephemeral key setup is also a way that might be allowed to avoid re-encryption. So again, it might be interesting to still study the possibility of an ephemeral key setup that doesn't use this. This also comes with a higher cost of performance, but it might be something viable in some particular use. This is the article that I quote during this presentation. And finally, I thank the Oracle project for making this able to happen. And thank you all. If you have any question, I will answer them now.
Thank you for your presentation. Are there any questions?
It doesn't affect it in any way because you generate a new public key for each iteration. Like, it's a very higher computational cost because you are performing like, you have to distribute your public key each time you want to establish a session key, but if your secret one is leaked, you don't mind because you are going to generate another one.
Okay.